All right. I was hoping to have a bit more time during the Chinese New Year week. That didn't quite happen. Um, you were probably busy with your own family um, obligations yourselves, and I know you. I owe you notes, and I wanted to produce a new set of slides. That's still coming, so it's still planned, and it'll happen at some point, but not yet. So for the time being, what I would like to do is continue with semantics. So we're going to talk about the virtual machine and its implications, right? So what do we do when we have a virtual machine? How does that help? So let's start by defining one, right? Virtual machines are generally inspired by hardware, by processors, right? Like the Pentium, or currently we don't call it the Pentium anymore, right? So it's the x86-64 architecture, or the ARM architecture, right? So we produce a kind of software interpreter for instructions that are extremely simple, right? And that turns out to be an extremely useful middle ground, right? It's an interpreter, so there's a loss of performance there, right? But the interpreted instructions are extremely simple, so the loss of performance is not significant, right? With new technology, those instructions can be compiled just in time, right? And that can make up for the loss of performance that as compared to a full-fledged compiler, right? But it allows you to control the execution in ways that hardware doesn't allow you to, right? It allows to trap errors and explain errors and trace back errors to the source code where the error was produced, right? And they significantly reduce the cost of software development. That's one thing that is extremely important. The other thing that is extremely important is that the size of the virtual machine code is significantly smaller as compared to the size of the binary executable that a compiler would produce, right? So you take the same algorithm implemented in Java and implemented in C++, and you look at the size of the bytecode that is produced by Java, it's significantly smaller compared to the exe file, to the executable file produced by the C++ compiler. If you want to transfer files across the network, if you want to have mobile code, right, that's definitely better, right? It makes transfers a lot faster. Because it is software again, and I was explaining about errors, but the errors are not the only thing that are easier to handle with a virtual machine. Security is a lot easier to handle. So now you have mobile code, it gets loaded into a virtual machine. It's a lot easier to put security checks in the virtual machine about the code, right? So the virtual machine becomes a very advantageous middle ground. There are trade-offs, right? The main loss is the loss of performance, but the benefits are so huge that it's always worth considering, right? There's yet another huge benefit. When you implement the same platform, like Java, let's say, right, onto a completely new hardware architecture, like, for instance, as handphones came about, right, and Android decided to have Java as a platform, right, for the underlying platform for Android, right? You have to take Java and port it to Android, right? So it turns out that the only thing that is that has to be ported is the JVM, is the virtual machine interpreter. The compiler stays the same, right? All the APIs pretty much stay the same. So there's very little cost in incorporating a new platform into, or a new piece of hardware onto a platform, right? The cost is a lot smaller. And the loss of performance, as I said, with the new advances in just-in-time compilation, it's something that, yeah, pretty much you don't need to worry about. There are a lot of platforms that use virtual machines. Java is probably the most prominent one, but now Python has a virtual machine. OCaml has a virtual machine, and then there is this thing that is becoming increasingly more pervasive called LLVM. Have you heard of it? All right. So LLVM is a strange thing because LLVM stands for low-level virtual machine, but it is a compiler backend. So it started as a virtual machine that was supposed to be compiled, not interpreted, right? But they established a layer of abstraction that was very much like a virtual machine. But then they added the ability to execute directly the code instead of compiling it into binary. And now there's all sorts of tricks and changes to this, to the point where the Java just-in-time compiler is based on LLVM, right? So in the end, pretty much every and GCC, right, the main C compiler nowadays compiles via LLVM into a binary, right? So LLVM becomes sort of a universal virtual machine. All right, so what do we want to do here? Give you a flavor of what a virtual machine would be like. Then, which means that we define it, we define instructions. We define how to execute the instructions, right? And then, how does that help us with the language that we have just defined, which is the language of expressions? How do we compile expressions into virtual machine code? So this is what we want to do today. Depending on whether we manage to finish until the end, we might go into the next topic, which is the next programming language, but we're going to just scratch the surface there. So it's a language. Languages are defined by inductive definitions. All right? So the simplest program that we can write, the simplest, and we're going to introduce instructions one by one, right? But the simplest, but we define the instructions by means of defining a program. So the simplest program we can run has the instruction done, right? Informally, we're going to see exactly what this means. But informally, this is the termination instruction. Once the virtual machine hits this instruction, it stops. All right? We're not at the phase where we have to explain what it is, but I'm just going to very quickly explain them so that it's not a complete mystery. We have two more instructions, LDC-I and LDC-B. LDC stands for load constant. I is integer, B is Boolean. And then those rules read as if S is a valid program, prepending LDCI dot to S. So that dot is like list concatenation or concatenating two sequences, right? LDCI followed by S is a valid program. LDCB followed by S is also a valid program, right? So if you think that done is a program, because that's what our first rule does, LDCI 10 followed by done would be a valid program. LDCI 10 followed by LDCB true followed by done would also be a valid program. This is what these rules are saying. What do they do? Informally, again, we're going to come back to this. We're going to have a stack machine, like the JVM. The stack machine has an operand stack, and typically it works by whenever we want to perform an operation, let's say plus, right? It pulls two operands from the stack, performs the operation between them, and pushes back the result, right? So all the operations work in this way. We don't have registers. Most of you probably have gone through a computer architecture module before, right? Where most processors have registers, we can address registers directly, right? And that's one way of performing computation, implementing computation. But a much simpler way is to have an operand stack, right? And each instruction does not have explicit operands. It goes to the stack, pushes as many arguments as it, pops as many arguments as it needs, performs the operation, pushes back the result. Okay? Now, we have to have an initial push of something in the stack, because if there's nothing in the stack, we can't perform any operation. So we're going to have these load constant instructions. We just push something on the stack, right? So let's say if we want to perform 2 plus 3, we're going to push 2, LDCI 2. We're going to push 3, LDCI 3, and then we're going to say plus, which pops 2 elements, pushes back the result. And then at the top of the stack, we have the result, right? When we hit done, whatever is at the top of the stack is the result of the entire program. That's going to be the convention. So let's keep going. If S is a valid program, plus followed by S is a valid program as well, right? So if S is done, plus followed by done is a valid program, right? So if I have LDCI 2 followed by LDCI 3 followed by plus followed by done, that would be a valid program. And we evaluate it, we expect that the result would be 5. The same with minus, times, division, and or not, LT, GT, EQ, and I might have left some out. There's also less, equal, greater, equal, I think. All right, there's also unary operations. Yeah. So is this clear so far? Right? So far, what you see is a way of defining syntax. I'm telling you what the instructions are doing, but that's just to keep you interested and not get bored yet. Right? Yes?
This does not guarantee, like, so for example, what if S is, one of the programs I have is just done, and then the next thing I put is equal done.
Yeah, no guarantees.
Oh.
The world explodes if that happens. You have to make sure that it doesn't, right? You have to make sure that you feed to the machine only valid programs. So, and here we're still a little bit following OCaml syntax. This sequence of instructions, LDCI 1, LDCI 2 plus done, would be a valid program, right? And formally, we expect the result to be 3, right? 1 goes into the stack, then 2 goes in the stack, then pop 2 operands, perform the plus between them, push back the result, done, finished. At the top of the stack at that point, we have the number 3. That's the result. But let's keep going and see how we actually define formally what, how to execute. Before executing, right, let's figure out how we compile. So we have an expression, and how does that expression become a program? So we're going to use a helper. The double arrow relation is the compilation relation, right? So it is defined from EPL, which is our language from last time, remember, to the EVML, which is the list of instructions which we just have seen defined on the previous slide, okay? And we need a helper. So the curly arrow is the helper compiler. And we're saying that if the helper compiler transforms E to S, then the compilation of E is S followed by done, right? So if you think in terms of code that we're going to write later, the double arrow takes the result of the curly arrow and appends done to the end. Clear? And we'll see we're going to understand immediately why this is necessary, because the helper compiler is a recursive relation, right? But we can only have one done in the program, right? So we can't have a done for every recursive invocation of the helper. Okay, so recursively, or the base case for this recursive relation is a constant translates into the instruction LDCIN, an integer constant. A Boolean constant translates into LDCB, and that constant. Right? So when I see a number, I'm going to put it on the stack. When I see a Boolean, I want to put it on the stack. Right? I'm going to push it on the stack. Easy. Now, if the helper compiler translates E1 into the sequence S1 and E2 into the sequence S2, then E1 plus E2 must be translated into S1 sequence, right? Followed by S2, also a sequence, followed by plus. All right? So we're abusing the dot here because the dot is an append between sequences as well as between elements or sequences and or elements, right? We're just assuming that whenever we're putting two things on the sides of a dot, somehow magically a sequence appears, right? So why does this make sense? Well, think about that, right? So if I want to evaluate E1 plus E2, I first must evaluate E1, and then I have to evaluate E2. So if I execute S1, I'm going to be left with the result of S1 at the top of the stack, right? And then this is a very interesting problem that this machine has. If I execute S2, after that, the execution of S2 will not touch whatever is already on the stack. This is a general property, right? S2 cannot touch whatever is there. So you can think of it as I'm making a copy of the machine and preserving whatever was there, right? I'm executing S2, and then the result of S2 is going to be on the stack on top of the result of S1, right? So there's this superposition, this non-interference between expressions that this kind of machine allows me to have. Right? I can bring a completely new expression and execute it on top of whatever is there. Whatever was there before stays as it was. Right? So now what do I have? I have the result of S1 followed by the result of S2. And then I come with a plus. So whenever I'm going to execute the plus, it's going to pull two operands, which are the results of S1 and S2, perform the operation, push back the result, right? So automatically I'm going to have the result of E1 plus E2. Is this clear? This is how the magic happens. Is this clear? Yeah. Same for times, same for division, same for minus, all right? And unary operations are going to have similarly, they're going to actually do similarly, just that they have one operand. So instead of pulling two things from the stack, I'm going to pull one thing from the stack, perform the operation, push back the result. So we have two examples. 1 plus 2 times 3 would be translated into LDCI1, LDCI2 plus, right? So you see that LDCI1, LDCI2, and plus, these first three instructions are the translation, the recursive translation of 1 plus 2. Right? Then I have 3. LDCI3 is the translation of 3. I have E1 star E2, right? So I translated E1, I translated E2, and now I have to translate the star times. And this is where the helper compiler stops. the helper compiler has been invoked recursively and produces everything up to times. And then the real compiler, which takes advantage of the helper compiler, comes and appends done. Why is that? Because we want to have a single done. If I wanted to make the done, I would not be able to append the done as part of a recursive computation, right? Because there are many invocations of that function, and you can't know which one should append the done. Similarly, if we say 1 plus 2 times 3, right? So we have expression E1 is 1, expression E2 is 2 times 3. So expression E1 translates into LDCI1. Expression 2 times 3 translates into LDCI2, LDCI3, and times. And then there's a plus between E1 and E2. This plus becomes this plus right here. And this is where the helper compiler completes its job. And then as we go back to the real compiler, the done gets appended. Is this clear? This is very similar to what you might know as the Polish notation, actually the reverse Polish notation, right? It corresponds to a post-order traversal of the syntax tree. Everybody knows what a post-order traversal is? Yeah? So if you think of the tree, you do a post-order traversal, right? So you first traverse the left tree, then you traverse the right tree, and then you traverse the root, right? So traversal is compilation. So we first compile the left expression, then the right expression, then you compile the operator. Questions so far? No? All fine? Yes? Well, we want to append this done here, right? The helper compiler is recursive. So you see this relation here depends on recursive invocations of the same relation on the sub parts of the expression. So if you were to express this computationally, you would define a function and say if my expression is of the type E1 plus E2, then compile E1 into S1, compile E2 into S2, and assemble the result in this way, right? So the current relation is defined recursively in terms of invocation on sub-parts of the current sub-expressions of the current expression. Because of the recursion, because of this method being invoked many times, you wouldn't know which of the invocations needs to perform the addition of the done instruction. Clear? So then you turn this into a helper, and then you're saying, yes, let the helper translate. This is the helper here. This relation here is the helper. And then the actual compiler takes the result of the helper and appends done. The compiler is only invoked once. Yes?
Why is the arrow the denominator not equal?
This one. But this is that's what we define here, right? Whatever is underneath is what we define.
So the double arrow is the process of compilation.
Yeah.
Right? And then the curly arrow is
The helper.
Compiler. But you're also converting E to S dot done. And that has to be done by a helper compiler. Right?
No, but we're reading it right. So E converts to S dot done if, right? So this is we're reading it bottom up, right? So E converts to S dot done if E helper compiles to S.
Then how about in the slide
Yes? So what's the trouble here?
So should we read it from bottom up? Say that.
Yes. So E1 plus E2 converts into S1 followed by S2 followed by plus. If E1 converts into S1 and E2 converts into S2.
So by the same logic, shouldn't the arrow in the denominator be a double arrow?
No. Okay, you've seen the code. I'll go back when we read the code. Actually, it would be a good time to read the code for this. Okay. It's when I see so little stuff on the screen as I connect to the projector. I can't quite know how to show what I need to show. So before we do anything else, when you load the project into IntelliJ, IntelliJ will detect it as a Scala project with SBT, and would also detect the fact that this is a grammar file which needs to have special treatment. It needs to generate its own code. This guy, which you see the grammar here, gets translated into some Java classes here. All right? This is not something that you really need to be aware of. I'm trying to explain a bug that is happening. All right? So this works all correctly, just that in this process, and these files need to be compiled, right? From Java, you need to go to class files. And everything happens under the hood, just that at the point of importing the project, all right, that folder, this folder here, so notice what it is, target and source managed. This folder is marked as sources root. And if that happens, you can't compile the project. It's a stupid bug. Okay? So what you're going to need to do is once the project is imported and SBT has run, you're going to see in the SBT console some stuff running, or in SBT shell, you're going to see some messages here at the bottom that some stuff is running. Once that finishes, you go and look for this folder, and if it's marked as sources root, so you go here, mark the directory as, and if it's blue color, then it's bad, right? And you say unmark. And as soon as you unmark, you will see that this one is actually correctly marked as generated sources root, at which point everything works fine. Okay? Now, if you don't want to work from inside IntelliJ, you can always go to the command line and say SBT test, and right, everything runs fine. Or SBT run, everything will run fine, right? Just that IntelliJ has a little bit of a problem in finding the compiled, the result of compiling Antler files because it marks that folder in the wrong way. Okay, cool. So now on to how we compile. So we have to define a virtual machine. So to the sources that we have already seen last time, we have been adding, these are the tests, sorry, we have added a definition of the expression virtual machine, all right? And we have to say what are the instructions, right? So we have to define instructions. So we create, as we did last time, a base interface or trait called instruction, and we have all the instructions that we have seen, we have them as subclasses of this instruction, right? So all of them are instructions. This definition is necessary so that we know what the instructions of the machine are. Okay, and then the denotational semantics is defined here. So notice what we're doing, and I'm going to change the file a little bit because it doesn't fit completely. Let me shrink this even more. Can I do it like this? Okay, in which case maybe, okay, maybe it works. So you see, I have the compiler, which that does what? Invokes the compiler helper and then appends done. Is that clear? Now the compiler helper is recursive. So what does it do? Well, if my expression, the expression that I need to translate, is of the form binary operation add between a left sub-expression and a right sub-expression, then compile the left, right? Compile the right, and then append the left, compilation of the left to the compilation of the, with the compilation of the right, and with the plus instruction. Yes? So look carefully at this rule. And then we're going to go to the rule on the slide. So look at this rule. We're going to look to the rule on the slide, and you're going to find that the left-hand side is below the line. No, sorry. How do we? It happens a little bit. It happens a little bit differently on the rule, right? So going back here, right? We're saying that it's like okay. Let's try to make this a little bit closer to what the rule looks like, right? So I could say S1 equals compiler helper left S2, and then we can say here S1 plus S2 plus CQ plus. Okay, so we're saying that, well, if the rule is of the form, right, left plus right, and in principle, to make it look like the rule, this is E1 and this is E2. Though it's not a good thing to use capitals for non-constants. Let's not use capitals. Confuses Scala. Confuses the highlighter. So E1, E2, right? So if my rule is of this form, then what do? Well, let me compile E1. Let me compile E2. So we're saying S1 is the result of compiling E1. S2 is the result of compiling E2. And the result of compiling this is this, right? So as you look at side by side the code and the rule, this is the reading that we have. Is this clear? Cool. Okay, so now also try to understand why we need to use the helper. right? So the compile uses the helper, which is recursive, and then appends done here, right? There's only one done. Compiler helper is recursive. So I have to use two functions. I need a helper. I can't do without a helper. Is that clear? Yes? All these other rules are the same. Okay, so let's ignore them for a while, right? Just look at this and look at the fact that I'm using the compiler helper. Is this clear? So the double arrow relation is implemented as compile. The compiler helper, the curly arrow relation, is implemented as compiler helper. Make sense? It's now clear that what's the relationship between the double arrow and the curly arrow?
The thing is that in the plus plus, the compiler helper is not doing anything. So compiler helper only converts E1 to S1 and E2 to S2. But in converting the expression E1 over E2 to the S1 S2 diff, compiler helper was not invoked.
So the compiler helper is invoked here, right?
Only at the numerator, not at the denominator.
At the denominator, this is the compiler helper at the denominator. The definition is the compiler helper at the denominator.
I can find you on the classes.
Sure. So I have to give it to Wayne Gunn. In OCaml, it would have looked a lot more, because the pattern matching in OCaml syntactically is a little bit different, right? So you would write compiler helper for every rule. I'm defining a function, and as I define the function, I define it as clauses. So I define a clause for compiler helper, and another clause for compiler helper, and another clause for compiler helper, right? So it looks like, right, because this is the curly relation. So it looks like the curly relation appears in a lot of places. Whereas in Scala, because the language is like that, right, I'm only saying, well, compiler helper is the definition of the function, but then what's on the left side here is a case, right? So compiler helper in case, the expression is of type E1 plus E2. Compiler helper in case, the expression is E1 divided by E2, right? But by nature of the syntax of the language in Scala, I only write compiler helper once, right? Whereas in OCaml or in Haskell, I would write something like this, right? I would say compiler helper of maybe a plus of E1, E2 equals blah, 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 right? Then compiler helper of minus E1, E2 equals blah, 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 right? So then I would have to write that compiler helper, and you would say, oh yeah, well, compiler helper appears for every rule, right? Now, in Scala, what we're doing is I'm not going to write compiler helper so many times. I'm just going to say of expression E equals E match, and then I say case plus, right? So the name of the function appears once, and there's many cases. But that's just a syntactic artifact, a syntactic trick. Okay. Now I did a lot of changes into this file. I'm going to show you one very neat trick. I can go into local history. So IntelliJ keeps and I can go back in time to 3 minutes ago and recover the old file. So I can just say, yes, all these changes that are no longer there, put them back. And then I recovered the file completely. saved my behind many times. This little feature. Okay, are we clear now? Cool. Let's look at a few tests. Tests, EVM test. All right, so how would we do generational semantics, this one. How would we test this? So something along the lines of assertive compile of parse of some input, right? And this is the output that we want, right? Something like this. We're introducing a lot of stuff about Scala in this process, and let's go through those elements. So list is the constructor for lists. We don't have the square brackets that are very typical in other languages. Why? Because that makes all the collections equal. There's no preferred collection, right? If you look at Haskell or OCaml, lists are square brackets. All the other collections, they have other ways of, more complicated ways of specifying. And that makes you go to the preferred one, which is the list all the time, but list is not always the most efficient one. The fact that you have to write list for list and set for set and array for array and so on makes them sort of equal from the point of view of the virtual the language, and therefore you're going to pick the right one all the time. So that's one thing. Another thing that we have introduced sort of surreptitiously is this operator ++, which is the concatenation between sequences, any kind of collections. Actually, it would work even between sets and a performed union. They can be put together with ++, right? Obviously, we have to be well typed. I think actually there is an operator here which is dot plus or plus. There is an operator ++ or colon ++. There's an operator that can add. I keep colon plus or. So instead of creating a singleton sequence, yeah, I think it's colon plus or plus colon. No, colon plus. So yeah, because I was rushing and I didn't have time to check. So a probably much better way of writing this would be to use this operator which appends a single element to a list, right? It makes for shorter expressions, right? So we have the append and we have the prepend operator is, if I wanted to prepend, is double colon. But if I want to use double colon, I have to use list, not sequence. But there should be plus colon. Yes, plus colon should work, I think. All right, so you have operators for prepend, for append, a single element, a list, and so on. Okay, and we're going to see sooner more sophisticated pattern matching on sequences. Is this clear? Looking at the code, is the code sufficiently clear so that everybody can do their homework as they, yeah? Okay, cool. Let's take a break before I forget.